Okay.
Yep.
Hi, everyone. Thank you so much for being here, and very grateful for this event. Definitely big thank you to WWC and Arabesque AI. Today, me and Isabelle are going to talk to you about the knowledge graphs. We will probably also refer to it as KG here and there in the conversation. So don't be confused when you hear it. So in terms of the outline, I will take care of the first half of this session by first introducing the concepts, ideas behind KG with some examples and use cases. And then we were talking about the construction of a knowledge graph. In detail, I would talk to you about the node extraction method. And for the second half of the presentation, Isabelle will present you the edge extraction method, followed by explaining how to use a knowledge graph to understand the stock market. I believe at the end, we will have a little bit time for answering some questions, so don't be shy. I hope you will enjoy this talk and find it very useful. So knowledge graph. It is a very popular subject in the field of AI and machine learning, along with a few other tasks in the field of natural language processing. We can probably imagine that this is mainly due to the rapid development of the internet and online platforms, where we more and more starting to create and share unique content, not only as individuals, but also organizations, which also made it impossible for any of us to ever keep up reading all of them, which is why we need automated natural language processing in order to extract a large amount of meaningful or relevant information in a very fast pace. We are now living in a situation that is data rich and information sparse. I'm not the first person who said this. And a larger proportion of the data we currently have are unstructured, such as the text data, images, videos, and memes, etc. It means that they don't have a predefined schema and types of its value like the structured data, so that it can be easily processed by machines and then become easily accessible to us. Therefore, a lot of the effort has been spent on how to extract, organize, as well as store information from these unstructured data. And because of this talk, you can probably guess this knowledge graph is the tool, is the very popular and very powerful technique for solving this problem. So first of all, what is a knowledge graph? As the definition shown here, a knowledge graph is a large network of nodes along with their edges. So the unit of a knowledge graph then, as shown here, is a tripole, which is two nodes linked by an edge. It's usually presented as entity one relation entity two, which is called a tripole. A node is usually represents an entity such as a company, a person, or a location, as shown here. And each of these nodes would have its own semantic types, properties, and relations to other properties. And these information are stored as edges, as we can see just from this screencast from Google. For the node Barack Obama, we have some property nodes such as was born on date, has gender, has family name, etc. And we also have some relation edges to other properties, to other entity nodes that are is politician, of married to, was born in, etc. So we can see that in this way, the knowledge graph can model real life information in a clear and human-like way. And some of the times these property nodes and the entity nodes are, how to say, the border between them is very small or blur. You can use them interchangeably, depends on what kind of knowledge graph you have. So now let's take a look at a more specific example. As we can see from this diagram here, it describes Microsoft is an instance of a software company, and the software company is an instance of business, and it produces software as its product. And here also, Wunderlist is an instance of application, which is a subclass of software. So we can see this small little knowledge graph is able to describe Microsoft and Wunderlist about what they are and what they do and how they interact with each other. For example, then we can consider a piece of news such as Microsoft bought Wunderlist. When integrated in the knowledge graph here like this with an edge, we can read the graph and understand that it is the software company, Microsoft, who has bought a software as its new product. And the software it bought is Wunderlist. And this also shows us the, the ability of integration of data. Imagine if we have more news, more entities, and more relations among these entities, we can easily attach them in, connect them, and there is really no limit how many edges and nodes you can have. For example, you can add Apple Inc., Oracle, because they are instances of business and with their own properties and news about what happened with them. You can extend this graph easily to 1 million pages, let's just say that. Some of you might have already thought about the structured data as well. You can include them in the same way into the same knowledge graph by adding, for example, CEOs, headquarters, and other financial or relevant information into this. Another cool thing about KG is that we can use it for reasoning and develop a new knowledge. For example, like what I've given here, with the relation A works for the HR team and B manages the HR team, we can logically derive the information, the relation between A and B, which is B being the manager of A. Another example is here. Another example is shown in the diagram. Wunderlist is rebranded as Microsoft To Do, for example, and Wunderlist is also an instance of application. Therefore, by looking at these two relations, we can logically conclude that the Microsoft To Do is also an instance of application. Because knowledge graph can be used this way to extract logical and structured information from unstructured data. It can be used to model information in almost any domain with any data type for the purpose of your task or downstream machine learning models. So when using a knowledge graph with machine learning and deep learning models, the decision path of the knowledge graph can help interpreting the model predictions, which helps with the explainability of our prediction model, basically to turn it from a black box into a transparent box. We can see what's happening inside. And also with this ability to derive new knowledge, we can use it potentially to help with zero-shot learning. And with the node generalization, we can potentially create a data set that is less specific and hence improve the data or help with the data in efficiency. Some of these benefits listed here. For detail, you can read this awesome blog that's written by, I forgot who, I think it's Mr. Chowdhury, and learn a bit more about how KG can be used to complement a machine learning and AI. Because KG is so powerful, many companies have already been using them. And in the literature, KG is also improved showed to improve some financial forecasting tasks. Here I've only listed a very few examples in this case. And they are obviously, they can also help with many other tasks. So feel free to dig in. Now let's look at some real world example. I think the most commonly known and perhaps the closest to our life is the Wikidata knowledge graph. It was first developed as the backbone of the Wikipedia project. Then it became more and more complete and is more and more frequently used as a knowledge base since it contains very comprehensive real-world information and very nicely and kindly being open source. By now, by last year, I think, Wikidata has over 80 million nodes collected and over 1 billion edges. It's very big and comprehensive, as I said. Here we can see in Wikidata, each entity is uniquely identified with a QID, London being Q84, to distinguish other entities that has the same name. And under the statements, we can see instance of being listed as one of the edge or property of London. In the entities listed outside there, these are the entities that are connected to London through this edge. And here is only one edge. If you scroll down to the actual page, you will see many more edges, such as London is located in, has mayor, subclasses of, and other information. And if you click on any of these entities, you would find their own entity page where each of them has its own QID and properties and related entities and so on. Here I want to show you what a property looks like. In Wikidata, they uniquely identified each of the edge or property with a PID. And they also have a page showing the information about what they mean, how they can be used, and how are they related to other edges. To search or query a knowledge graph, as demonstrated a minute ago, you will typically need a node to start with or to arrive on, and an edge to walk through. The number of edges you walked through are commonly known or referred to as hops, and the act of searching through information by walking down a number of edges is called graph traversal. Today we are not going into too much detail about this, but just so you know about the concept of searching in a graph. So what are some of the real world use cases of knowledge graph? Again, I think the most intuitive is question answering through, because knowledge graph can be used for reasoning. For example, when we ask a question, what are the genres of movie written by Louise Malice, we can first, in our knowledge graph, find the node Louise Malice and travel down the edge written by to find a number of movies. Here, we might also need a filter if he also writes some other stuff like books, plays, poetries, etc. But with all the movies nodes we have, we can then travel down the edges, for example, hashtags, which would give us another group of nodes, and then we can use them again to find more nodes until we finally arrived on a node that can provide us with a satisfying answer. A similar process can also be used to help search engine to understand the intent of a user's search question, which can then help create a standard query, for example, a SQL query to search the backend structured database in order to provide an answer back to the user. Another example is that you can create a knowledge graph for your specific purpose or your business. where you can include information about your product, their properties, features, your customers, and their preferences, taste, background information, etc., and how they interact with each other. Then this knowledge graph can be used to analyze things like a behavioral patterns, similarities between the interests of your customers, and maybe also feedbacks and reviews. Then this information would be able to help you to recommend your product to relevant customers in order to maximize the chance that they will use or buy the product that you are recommended, that you recommended to them. You can also run algorithms on your knowledge graph, for example, a clustering algorithm to identify things like themes, communities, trends, by looking at some of these clusters. And depends on what domain of your knowledge graph is in, these kind of analysis can potentially help with supply chain management, dynamic risk analysis, or thematic investing. So now we know we need a knowledge graph, and we need to know what kind of knowledge graph we need for our specific research topics or tasks or project or personal use. How do we build one? First, what we need to do is to convert the unstructured or semi-structured data into node and edges. And these are some of the steps that will be involved in this. Typically, a named entity recognition method is used for extracting what entities are involved in our data. And to link them, we will have to explore what are the relations between our relations, and is usually achieved with relation extraction and information extraction techniques, which will be introduced by Isabelle later. And for each entity, we might also need to know what kind of properties or attributes they have to extract this kind of information. We can perform entity linking, for example, to a real-world knowledge base, such as Wikidata I just introduced. And this type sometimes is also referred to as entity alignment, which is to figure out which real-world object the entity in our knowledge graph is referring to. Or we can also manually annotate or find out some of these attributes that belongs to our entity, or we can use in an internal knowledge base where we have more specific and more private information that are facts, informations about each of the entities are involved. If we do have structured data as well, we might want to incorporate them by establishing a map between entities in our KG and entities in our structured data. This is to enrich the representation or the information contained in our entities. Once we have this information, we can construct our knowledge graph, which we can then use it for a number of downstream tasks, for example, modeling, feature extraction, or reasoning, or if it's just a pure open source knowledge graph like Wikidata, we can display it and allow people to search for it and build a front end, etc. If for more detail on this specific steps, once again, I will refer to this awesome blog written by Agatha Muka, and which is also where I bought this, what I borrowed this very nice diagram. So next, let's look at specifically how to extract entities. In the field of natural language processing, the task of extracting entities from text is known as the named entity recognition task. As shown in the example here, an ER model is able to identify entities and provide them with a general entity label. For example, these two are identified as person. This complete EC library is a miscellaneous. Airport and London is identified as location. But they are able to do it accurately and correctly, but there are also some problems. For example, as we can see, both for the person case, both these are identified as person, but we are not able to distinguish whether Russ Cochran is the American golfer or the publisher. And similarly, we cannot make sure if the Steve McQueen is the actor or the director. Also for the two location entities, we can see they are both just labeled equally as location. But in some cases, we can imagine the London could be a more important location information than airport, or vice versa in some other cases. So we can understand that for the purpose of creating knowledge graph using these general entity types, it's not enough for our knowledge graph. What would be more useful here is to label Russ Cochran as the publisher, the writer, and the person, and label these EC library to be the project, the reprint project, the comic series, a work of art, etc. So each of these entities with their labels and attributes can carry richer information from the labels themselves. Additionally, these specific labels would then can potentially show some semantic relations with other entity types, such as the publisher can be the creator of a book series or artwork or newspapers, and the iPhone being product of the Apple Inc., and police and criminal are usually enemies. And as introduced before, to retrieve these specific information, we can annotate using internal knowledge base or connect them with a external knowledge base. In our case, I will showcase you how to link these entities to a external knowledge base, which brings us to the next slide. As the method used to achieve this task can be broken down into 3 steps. The first step is entity boundary detection, which is to extract potential entities from the text. We can use a simple noun phrase detection or an NER model as introduced before for this task. And by potential entities, I mean that the entities we extract from the text may or may not exist in the knowledge base. For example, you and me, we are entities, we are person entities, but we might not have a Wikipedia entry. And as we can see from the diagram on the right here, the headline example, how Amazon is holding Seattle hostage, we can use a named entity recognition model first to extract Amazon, Seattle, and hostage to be the potential entities. And then we need to figure out what they are in the real world. To do that, we need to first find out all the options of what they might be. Practically speaking, this is to find all the entities that existed in the knowledge base that has the same name or aliases of the identified entity in the headline here. To reduce confusion, we usually call them candidates instead of entities, and therefore this step is usually referred to as a candidate generation step. Once again, we know that we are going to use Wikidata to help with this step because it has the largest collection of real-world entities, and also it supports a Wikipedia where it's freely available in many languages. So now let's take Amazon as example to walk through this process. First, we search in the knowledge base how many Amazon candidates we have. And by name and aliases search, we found 6,000 entities, which means among these 6,000 Amazon candidates, one of them is what this Amazon in the title referred to. And we need to figure out what this entity is. And that is our next step, which is the entity disambiguation step. I believe as humans, we can tell that the Amazon here is referring to as Amazon, the company, because we understand the meaning of them, which means somehow we also need to represent the meaning of these entities and make our machines and computers understand it too. But how do we learn the meaning of something when we don't know about it? That is a question, $1 million question. We typically Google it, and then somehow a Wikipedia page might show up on the first results, and you click on it, read it, maybe read a piece of it, then you understand. So here we can pretty much do the same thing. We can use the text from the Wikipedia page for each of the entity to represent the meaning of the candidate, and we can use the context to represent the meaning of the entity of targets. In this case, it's our headline. In some other cases, it might be an article or something, or news. And once we gathered these text, we can transform them into a vector representation using some techniques such as TF-IDF, word embeddings, or some other metrics. You can really be very creative here. As long as it matters, it makes sense to your problem, it will perform. And from here, then we can measure the similarity between each of the candidate vector against the context vector. And the candidate with the highest similarity score would be the candidate that is most likely to be referred to by the entity in our input text. So now that we know what the entity is, meaning it is Amazon, the company, and not rainforest or any other things, we can search the Wikidata knowledge base again to find the parent and grandparents of this entity, and use their names as a label to describe from the most specific to the most general what this entity is. In our case here, we can see that first we have Amazon being the Amazon, the company itself, and it is also a website, business, enterprise, and the giant of the web, etc. This process is also applied to every single entity's potential entities in the input text. Here, I'm just going to show you quickly what they look like. And we can see they are linked. Each of them are linked with the Q identifier from Wikidata. And each of them have a bunch of labels. And the L0 label is the most specific, referring to the entity themselves. And the L1, L2, L3 labels being the name of the entity that are at 1, 2, 3 hops away from the base entity. And the edges we use to retrieve these entities are instance of, parts of, and subclasses of. In your case, you could use other edges to retrieve relevant information, but here is just to showcase how you could involve a knowledge base to enrich your own knowledge graph. And why do we need these labels? Once again, we can now actually search in our knowledge graph with a very specific name, very specific information to retrieve some nodes, for example, the ID or the actual name. And we can also search for all the node with some general information. For example, I want all the business or organizations, I want all the cities, I want all the person node in our knowledge graph. We'll be able to retrieve them with these extra information added on. Of course, we can travel further into the knowledge base to retrieve more information about each of the entities involved. And needless to say that this choice depends on what do you need, what is your purpose, and what do you want to do with that information. So now that we have the method for extracting nodes and link them to a real-world knowledge base, I will give the floor to Isabelle to talk about the edge extraction method next. Thank you.
Thank you, Mabel. I will start sharing my screen. Just maybe quickly, we'll answer questions perhaps at the end, but I've seen two so far that I can maybe quickly answer. So the advantage of searching, if you're searching, I mean, you can do many more things than search for similar entities in a KG, but if that's what you're using it for, I would say the difference between using embeddings or like traditional embedded word embed or sentence embeddings, or even language models such as BERT, and using KG is that you're doing it in a more explicit manner. So BERT will maybe include some knowledge about how things are related, but it will be noisy. Whereas if you're looking, for example, for headquarters, this is a binary. There are binary features that will define what headquarters are. It means it is the main location for a specific company. Whereas if you're just if you were to embed a city and look for similar cities, you may not be able to find. Basically, it will be a more noisy search process, whereas here you're explicitly modeling the kind of structured information to be included. And then the other question, I think, was how to contextualize nodes. And as Mabel was explaining, you will have different nodes depending on the entity linking. So the Amazon, that is the forest, will be a separate node from the Amazon, that is the company, and they will have different contexts in that they will be linked to different entities. I hope that helps, but we can definitely go back to that at the end. So now that we have our entities extracted, how do we extract relations between them? Because the point of having a knowledge graph is to have this information in a structured way, is to know how these entities are linked, as opposed to just having a bag of words or even having embeddings. So it really depends on the data that you have available. If you happen to have a nice big knowledge base, such as Wikipedia, where you have lists of pairs of entities for a specific relation, then you can use what is called the distance supervision to train a model to identify these relations in other pieces of text. So the way you do this is you gather pairs of entities for predefined relations from a database, and then you find sentences that contain both entities, and you assume that every sentence that contains these entities expresses the relation, which is a noisy assumption, but in practice it works most of the time. Then you will tag these entities to tell the model these are the bits of the sentence I want you to focus on, because obviously you could have a sentence with 3 entities, and so the same sentence needs to be tagged differently if you want to tell the model, I want you to model the relation between these 2 entities, or I want you to model the relation between 2 other entities in the same sentence. So you need to tag them, and then you use a model. In our case, we used BERT, which is this, probably most of you will be familiar with, large pre-trained model that you can fine-tune for a downstream task. In this case, you will use the model to create an embedding, which will be the last layer of which will be fine-tuned for your purpose. And then there's another layer of weights that will produce predictions so that you can have a distribution over all the possible relations. And then you give the model many examples of all the relations that you want to be able to predict, and you let it learn how to do this. So this is a fully supervised technique, even though the supervision is distant, as we said. And as you can see, you have the entities tagged in the sentence, and you'll have a label that expresses the relation, including a no relation label. And then we fine-tuned our BERT model, the last layer of which was just a softmax, so just a distribution of probabilities across all the relations that you've given it pairs of entities for. And then once you've trained your model, you can give it, you can use it to embed a new sentence, and then it will predict a relation for you. So this is, you can see the list of relations that we can have if we use such a supervised technique. But then, of course, that assumes that you have those pairs of entities for every relation that you want to predict, which is not always the case. You may have relations that are, for example, not in the knowledge base that you're using, not in Wikipedia, but you would still be, you would still like to be able to extract these relations, and they are still predefined. Then what you can do is you can leverage transfer learning to extract those relations. So you can, instead of training the model to extract the specific relations that you want to be able to predict, you will train the model on a similar task. For example, extracting other relations. So you train it to extract the relations that you do have pairs of entities for from a knowledge base. And then you will use the model trained in this way to create embeddings. And you use a similarity function rather than directly predicting the relation. You will embed the target vector, so embed the sentence that you're testing, embed some examples of the relation you're trying to predict, and say, okay, ask the model, okay, how close are these? And what is the closest relation that to the embedding that I've produced for my target sentence? And that is how you pick a relation. So it's less specific to the relations you're trying to produce. But in practice, depending on whether the relation your target relations are close or less close to the relations that the model has been trained on, it will work like more or less well. But in practice, it also works. A third possibility, if you would like to not use any labeled data at all, you can also do what the Google team did, which is just use the distance supervision assumption directly. Going into a large corpus of text. Here again, they use Wikipedia, but you could use something else. And then say, okay, every time that I see the same entities together, I am going to assume that this expresses the same relation. And every time that I see different pairs of entities, I'm going to assume that this expresses a different relations. Obviously, this is not a foolproof assumption. You will have times that the same entities are actually in a different relation, and you will have time where different entities actually express the same relation. But broadly, I think they also use a few heuristics to filter the data when they're labeling it. But broadly, if you have a large enough corpus, it works. So you pair sentences that contain, so they use BERT here again to do sentence pair classification. So they take one sentence that has the same entities, two sentences with the same entities. They say this is a positive example, this expresses the same relation, and then they take two sentences that have different entities, and they label that as a negative example. And they train it quite extensively. They actually retrained BERT, so this is not fine-tuning. So obviously, if you're Google, you have the resources to do that. It's maybe a bit trickier if you're not Google, but this is if you really don't want to have to use any labeled data at all. And the cool thing is that actually, once you've trained your model in that way, it is able to identify a very large range of new relations that you give it. And it can do that with very few examples, and even more efficiently than if you do transfer learning. So that works quite well if you have the resources. So what happens if you don't have, you not only don't have labeled data, but you don't have a predefined schema of relations. So you don't really know which relations you're looking for, which actually may apply to a lot of domains. Then in that case, what you can do is, instead of doing supervised relation extraction, you can do open information extraction, where you extract information from the raw text without a predefined schema, and you use the text to structure the relation. So in this case, we have, for example, Apple agrees to pay 500 million. And so you, from the raw text and using the syntactic tree, so the hierarchical, linguistic hierarchical structure of the sentence, you extract information in the form of triples, where you have entity, relation, entity. And you can link them. So here you see that we have one triple that is embedded inside another triple. So a triple is considered as a node, as an entity. And if you use syntactic information like that, you can extract triples in this way. Obviously, it means that downstream you may want to use some techniques to formalize the relations between, because every time you have a different predicate, you will end up with a different relation. But as a first step, you could use, and that's what we do, use the main verb as a rough proxy for the type of event. So what the syntactic information gives you is what is mainly going on here. And for example, in the following sentence, Facebook data breach hits 50 million users, also affects users who use Facebook to sign. You can see that you have 4 verbs here. And if you're just using the raw text, or even if you're using a language model embedding, it doesn't tell you explicitly what is the main event. But if you look at the syntactic tree, you will have a main verb, and that will be hit. So the main event here is a hit. Now, obviously, you also have the context for that, but it gives you like a first way of categorizing the types of events. There are some weaknesses to doing this. If you are using a parser, you may get a lot of errors, especially in our case, this is news headlines, and news headlines often are missing verbs. They use ellipses. They have a lot of caps in places where you wouldn't expect them in normal text. Another thing is, obviously, syntactic structure isn't always a reflection of semantic importance. So the main verb might well, in some cases, just not be the main event. there is no, you will have to find a way around trying to map this with a formal database, because there is no straightforward way of mapping the raw text with a formal schema. And then using the verb alone isn't always enough to describe the event. Obviously, you need the context as well. But you can combine this. So you can use this information on top of more fine-grained contextual information. And you can combine them, for example, in a structured embedding. So what do we use this for? Well, we work in finance, so we use it for financial purposes. That is the sort of downstream goal that we use what we extract from the knowledge graph for. But once you have built your knowledge graph, there's a range of things that you can do with it. You can, as we mentioned, normalize the edges. So you have your predicates that have been extracted using open information extraction, that you can try and map back to the formalized relations that exist in Wikipedia. You could cluster events together or triples together, so that you would categorize types of events. You could train a model to produce event embeddings. So the way, I'm not going to get, because we don't really have the time to do that, I won't get into details here, but to model, to produce embeddings for events, you have to use a different technique than the usual sort of vanilla BERT embeddings, because the language model hasn't been trained to really combine structured information together. It uses the whole of all the words in the sentence, and the way it embeds them is from what it's learned, from the way it's been trained, but it hasn't been explicitly trained to, for example, combine a subject and a predicate, and then on the other end, the predicate and the object, and then sort of combine these two together, which is what an appropriate event embedding neural network, which is called neural tensor network, will do. But that is, if you want to read more about that, read about neural tensor networks. It's really cool. What else can you do? You can try and gather analytics about, you can do analytics on your graphs. Okay, what are the kind of entities that occur together? What are the kind of edges that are associated with those entities? You can probably gather already a lot of knowledge from that. And then the final thing that you can do is produce graph embeddings, which means instead of just embedding the sentence or the triple, which is what you would do with a normal language model, you can say, okay, I want to embed actually the sentence that contains the event plus everything else that I know about the entities that are involved in this event, which obviously gives you a lot more information to use in downstream applications as features. So there are many features that you can get from that. And yeah, I mean, it in this very raw form, it looks like this, which doesn't say more, but it's also, as a first step, if you do open information extraction, the disadvantage is, of course, it's very noisy, but the advantage is that you can do all kinds of hops and all kinds of edge retrieval from there. You can choose, you can say, okay, I only want the subject, the object, the predicate, I don't care about anything else. Or you can say, actually, in a certain case, I want to model all the modifiers, so everything that has been applied to Apple as an entity, I want to know, so I want to use that as feature. Or, I mean, there are many possibilities, and yeah, it depends on what you want to do with it, and how much feature engineering you're prepared to go into. But down the line, you would then combine these features with your finance model. So you'll probably end up with a model for the stock market. You have to take into account order. You're dealing with time series most of the time. And so you'll probably have a model such as a CNN or an LSTM, which are networks that will take into account the time component. So they will be modeling both the financial time series that you're feeding them, plus the text or news information, for example, still keeping this temporal aspect to it. And that will be the most efficient way of modeling it. So we are at this stage, we are where we have produced those features, and we are the next step will be to integrate these into our usual models for financial prediction, and then see how we do in terms of improving the predictions that come out of the models. But I believe this is the conclusion to the presentation. I think I'm not sure how we're doing in terms of time. I will ask the organizers to tell me.
Yeah, I mean, we're about at time, but
Oh yeah, actually, that wasn't too bad. Sorry, I hadn't looked at it.
Fine. And some of the questions have been being answered as you're speaking, just in written form. But if folks still have some questions, I think we can take a couple extra minutes and just, if there's any questions out in the audience that need to be asked, please ask them. Yeah, so
I see the normalizing edge question. So yeah, if that hasn't been answered, I mean, for example, if you had I don't know, some sentence that mentions makes cars, produces cars. In both cases, you want to have an edge that in Wikipedia would be has product X. So you would like those two raw text predicates, which are different predicates but mean the same thing, to be bundled together into one formal relation. So if you have like a formal schema, they'll be part of the same thing, and you can train a model to map both of them. If you're using the first supervised technique, you would be mapping both of those predicates into the same Wikipedia normalized or formalized relation, if that makes sense.
Thanks for clarifying that.
I see a question about research internship. We do I don't know if I'm the best person to answer this. We do actually Sophia might be. We do research internships, so I'm not sure if we are at the moment actively still recruiting, but again, Sophia is probably better able to answer that. We definitely have a few interns at the moment, I think. Still. Mabel, do you know more about this?
I did ask, and the answer is yes, we are hiring, and also engineers as well. People are welcome to contact us if they are interested in our research and know more about us as well.
Yeah, absolutely.
Yeah, and I can see that Ben is in the chat just saying to point internship folks that way.
Okay, we will send them en masse to him.
Are there any other questions from anyone in the audience? I know there's been a lot of information here today, and it's been a really good presentation. The recording should be up in the next couple of weeks on Women Who Code YouTube, since that's often a question. We just take them and we we make sure that the beginning and the end is all clean and that nobody has, put anything on screen that would be inappropriate. I'm sure it'll be fine, but everything just goes through our little processing at the end there. So that's why it will not be up immediately. I don't see any other questions coming through the Q&A. So I just want to thank both of you for your time. We've got some folks thanking
thank you guys.
Sorry, I'm just sitting here being a voice in the void. I didn't realize. Here's my face again. Yeah, I just want to thank you both for your time and for sharing this great presentation with everyone. Did you want to say anything else to wrap up today, Sapphire?
I want to say thank you. It's been fantastic talk, and I'm so excited to share it with the community afterwards for all the people that couldn't make it. So yeah, we'll post that when it's available.
Cool. Yeah, it was. Thank you for the opportunity to give the presentation. It's really nice.
Yeah, thank you.